Hello everyone, today we are going to talk about the Astable Multivibrator, and we all know that Astable Multivibrator is a multivibrator circuit that is not stable. So we are going to go about the Astable Multivibrator. Two transistors named Q1 and Q2 are connected in feedback to one another. The collector of transistor Q1 is connected to the base of transistor Q2 through the capacitor C1 and vice versa. So what we are meaning is that the collector of Q1 is connected to the base of transistor Q2, and the collector of Q2 is connected to the base of transistor Q1. The collector load resistors R1 and R4 and the biasing resistors R2 and R3 are of equal values. The capacitors C1 and C2 are also of equal values. The next one is this is the construction of a stable multivibrator. We have C1 capacitor C1 connected to the base of transistor Q2 and capacitor C2 and R3 connected to the base of transistor Q1. The emitter of the both transistors are grounded. So R4 is the one that biases the collector current of transistor Q2, and R1 is the biasing of this transistor Q1. So in this circuit, as we can see, is that when operating in this circuit, C1, when it reaches to, because the two transistors are alike, so when C1 reaches it's the biasing voltage of transistor Q2, which is 0.7, the transistor Q2 start conducting, which makes it narrows the conduction of transistor Q2. Hence this transistor becomes into saturation mode while Q1 is in cutoff mode. So as this capacitor is draining, capacitor C2 charges through resistor R4, and when it reaches the biasing voltage of the transistor, it biases transistor Q1, and capacitor C1 start charging through resistor R1. So this makes the transistors to be in on and off state of the transistor. So let us see the operation of these transistors, how they operate. So the operation of this transistor, the operation of a stable multivibrator. When VCC is applied to the collector current of the transistors increases, because as the collector current depends upon the base current. This is where IC is equal to beta times the IB of the transistor. As no transistor characteristics are alike, one of the transistors, say Q1, has its collector current increase and thus conducts. So when it starts conducting, the collector of Q1 is applied to the base of Q2 through C1. Hence, this connection lets the increased negative voltage at the transistor of Q1 to get applied at the base of Q2, and its collector current decreases. As these continuous actions makes the collector current of Q2 to decrease further, this current, when applied to the base of Q1, makes it more negative. With the cumulative action, Q1 gets into saturation and Q2 to cutoff. Thus, the output voltage of Q1 will be VCE at saturation, and Q2 will be equal to VCC. the capacitor C1 charges through R1, and when the voltage across C1 reaches 0.7 volt, this is enough to turn the transistor Q2 to saturation, as this voltage is applied to the base of Q2. So when the capacitor C1 reaches the 0.7 volts of the bias, this is 0.7 volt is the voltage that is used to bias the transistor so that the transistor can start conducting. This reduction of voltage at point B is applied at the base of transistor Q1 through C2, which makes the Q1 reverse bias. So when Q2 start conducting, Q1 is in reverse biased. As of this series turns the transistor Q1 to cut off and Q2 to saturation mode. Now at this point Q2 is in saturation mode. Now point A has the potential VCC. So point A is equal, the VCC is equal, at point A it is the potential is equal to VCC. The capacitor C2 charges through R2 the voltage across this capacitor C2, and when it gets to the biasing voltage of the transistor Q1 it's in saturation, and now the transistor Q2 is in cutoff mode. So this action keeps on repeating itself. Hence the output voltage and the output waveform are formed, and they look like in a square because one transistor is in off state when the other one is in on state. They keep interchanging. The time period of this on and off states depends upon the values of biasing resistors and capacitors used, i.e. so the on and off state, it depends with the values of the resistors you are using and the capacitor you are going to use. As both transistors are operated alternately, the output is a square waveform with the peak amplitude of VCC. So we have the waveforms that are formed. This is the waveform that is formed after this when the collectors of Q1 and Q2. This is the waveform. We have the square waveforms. When Q1 is on, Q2 is in off state. When Q1 is in off state, the Q2 is in on state. So we have the square waveform. These are the waveform formed after we feed our transistors with the VCC in. The formula to calculate the frequency of oscillation is as shown. So the on time of transistor Q1 on the off time of transistor Q2 is given by T1 is equals to 0.69. Then you multiply with the value of resistor R1 and C1. Similarly, the off time of transistor Q1 or on time of transistor Q2 is given by, so T2 is the 0.69 multiplied by the R2 and the value of capacitor C2. So the total time taken to complete one square wave, it is equals to T is equals to T1 plus T2, which can be given by 0.69 with the biasing voltage of the transistor. You multiply by the value of resistor R1 and capacitor 1 plus value of resistor R2 and the value of capacitor 2, as R1 is equal to R2, and so R1 is equals to R2, which is equals to R, and C1 is equals to C2, which is equals to C. The frequency of square wave will be given by 0.69. You multiply by 2 times RC, which will give us the 1.38 RC, so which is approximately 0.7 multiplied by RC. So this one is the formula for calculating the frequency of oscillation. Now we have the applications of Astable Multivibrator. Astable multivibrators are used in many applications such as amateur radio equipment, Morse code generator timer circuits, analog circuits, and TV system. This is the end of the presentation. Thanks for watching the video.